Class, well, welcome to chapter 2, which is called The Chemistry of Life. So we're going to begin talking about a lot of chemistry topics here within the next few chapters. Basically, chapters 2, 3, 4, and 5 are all going to be chemistry. We'll first do a little bit of like basic, very basic, like inorganic chemistry, and then we'll move in, which is in this chapter, and then Chapter 3 is going to move into like water chemistry and pH. Chapter 4 is going to move into organic chemistry, as well as Chapter 5 is also going to cover organic chemistry. So some of the topics that we're going to begin talking about, for example, the chemical properties of why this little water strider bug is able to walk on water. And so what is this property of water that allows this little insect to do this? All right. So you ask, why do we need to study so much chemistry in the biology class? And this is what usually gets students who are like, why so much chemistry? And it's interesting because a lot of schools around the country and even around the world, they usually require students to have chemistry before they take biology class, especially like this magnitude of biology class, like a major's biology, or even take it concurrently. So chemistry is a huge part of biology. And why is that? Like, why do you need to study chemistry in a biology class? Well, because if you think about it, life runs on chemistry. Like, we are all chemistry, right? Like all of our reactions, the molecules that make us up, we are all chemistry. So it is vital to understand at least basic chem and basic organic chemistry to understand how biological systems work. All right, so that is our first question, I believe, on our follow along guide. So why study chemistry in a biology class? Because living organisms are all chemistry. The molecules, we'll just say, for example, the molecules that make us up and the chemical reactions that run the work of living, for example, just in a very general sense. All right, so a lot of this hopefully should be a review, right? Because this is very basic. I mean, this is chemistry that you will learn even in like elementary school, middle school, right? So what's matter, atoms, etc. So hopefully this is just a really good review for you. If this is not a review and you're really struggling, not getting ahead of the game with the chemistry can really set students back in this class. I just want to make that note. So try to get as much tutoring or extra help, or just review this as much as you can, because if you really like slack on the chemistry part right away, this all builds, the whole class builds. So chapter after chapter, we're just going to kind of build on these chemistry topics. And even though like these first few chapters are like directly studying the chemistry, the chapters that we do later on, we talk about metabolism and respiration, photosynthesis, even like cell division, DNA replication, right? It all builds on the basic chemistry facts. So you really want to make sure that you get a really good handle on this, whether it's going to tutoring or just getting extra review. Okay, so I like to throw this slide in here just as a good example for living organisms using chemistry or using chemical molecules, right, as like part of their biology. So this is a type of carpenter ant, and I was just showing here that how they use, for example, formic acid. They're able to secrete out formic acid to protect themselves against predators and other microbial parasites. So formic acid is a chemical, right? So it's chemistry. So I just wanted to show you like how that is incorporated into a living organism. Okay, all right, so let's start from the basics. So what is matter, right? Matter is the main thing, right? The basic thing here. So what is matter? Matter is anything that has a mass and takes up space. So let's write that in our thing. So matter is anything that has mass and takes up space. Okay, and matter is also the most basic building block of life. Okay, so then what is the difference between mass and weight? Because that is always a question that I get, right? So if matter is something that has mass and takes up weight, what is the difference between mass and weight? So mass is the amount of substance that you have, the amount of matter that you have. And weight is something that has to do with gravity. So a good thing, like, so for example, like if there was no gravity, you wouldn't have any weight. So think about like if you're in space, right? There's no gravity in space. Gravity is like a force that we feel here on Earth. So if you're in space, you're going to have the same exact mass. You have the same amount of substance or matter that makes up your body, but you're not going to feel any weight. You don't have any weight because there's no gravity pulling you down. Another good example of that is like, let's talk about the moon. So the moon has 1/6 less gravity than Earth. So you would actually weigh 1/6 less than you do on Earth, right? So wouldn't that be amazing? So that's the difference between mass and weight. All right, so mass, we said mass is the amount of substance or matter that something has, and then weight is the effect of gravity. And then, so we'll say, example, you would have the same mass in space, but no weight. No weight because no gravity. Okay, awesome. All right, so that should be a good review, basic review. So now what about the states of matter? So there are 4 states of matter, right? When we think about 4 states of matter are obviously solid, liquid, gas. Everybody's heard of those, and also plasma. So plasma is maybe one that you have not heard of. Plasma is beyond a gas. So plasma is ionized gas, and this is due to missing electrons. Like, so they're charged atoms, they're ions at this point. And so we're going to get into it in a little bit about what are the subatomic particles of an atom. And so hopefully you remember like protons, neutrons, electrons. Hopefully you remember that electrons like orbit around the shell of atoms, and those electrons can be ripped off of atoms, they can be added to atoms. And so anytime an atom is missing an electron or gains an electron, it is called an ion, and they end up becoming charged because electrons are negatively charged and protons, which are in the nucleus of an atom, are positively charged. So when you take off an electron or you add an electron, it produces a charge difference because you're going to have a different number then of electrons or negatively charged particles versus positively charged particles. So it's going to give you this charge difference. So those are what ions is. So then when you talk about an ionized gas, that's what those are. So we're going to get into that in a little bit here. So some examples of plasma that you've seen or you've heard of, the aurora borealis, or the northern lights, neon fluorescent bulbs, lightning. So those are all examples of charged gas, which is plasma. So for example, like with the northern lights or the aurora borealis, so this is when the UV rays and different particle rays from the sun come in, and they're super, super hot. So they're super energized, and they're able to disrupt the atoms of the gas that is in our atmosphere. So then these ions will be produced, right? So these charged particles will be produced from the gases that are in our atmosphere, and that's what the aurora borealis is. So very, very cool display of how we can look at that. And so when we look here at the 4 states of matter, these are things that you probably have also heard of or seen before. Should be a review when we're looking at a solid, a liquid, and a gas, and then plasma. So for example, if we're talking about like the states of water, so water in an ice state is very, very cold, right? We're talking about like below 0 degrees Celsius is freezing. The molecules are very, very slow. They're not moving. They're fixed in kind of like this lattice. They take the structure of like whatever, they'll take the structure of whatever container they're in. So for example, if you freeze water, right, we know that we can make ice cubes, right? They're solid. They take the structure on the shape of whatever container they're put into. And then liquid is going to be a little bit warmer, and we're talking about 0 degrees Celsius, which is freezing, to 100 degrees Celsius, which boils. So it's somewhere in between there. And we know that liquid water has more movement, right? So it can like move, it's free to move, right? In whatever container that you have, it's not as fixed as a solid, and then not as like loose and movable as a gas. And then a gas is going to be really, really hot, supercharged, moving really, really fast. So this is anything that's going to be above 100 degrees Celsius if we're talking about water, right? So there's other chemicals out there that will turn into a gas or turn into a solid at different temperatures. These are just ones for water. So here molecules are moving really, really fast. They're large, spacing, etc. And then plasma is going to be an even hotter, right? So we're talking about over 100,000 degrees Celsius, really, really fast moving. And this is where the energy is so intense here that these molecules or these atoms are able to become ionized. So they're going to end up like losing electrons, gaining electrons, right? Because it's just moving really, really fast. All right, so those are our 4 states of matter. Let's go ahead and fill out our follow along. So we've got solid, liquid, gas, and plasma. An example and characteristic, we'll say cold, ice, we'll say below 0 degrees Celsius, tightly packed. Tightly packed water molecules. All right, and then liquid, we're going to say a little bit warmer. This is going to be 0 degrees Celsius to 100 degrees Celsius. More free moving. Takes the shape of the container. Okay, and then gas is going to be hot. This is going to be 100 degrees Celsius or beyond, and they're fast moving. Okay, and then plasma is going to be really hot, 100 degrees Celsius plus, super fast moving, ionized gas atoms are formed. All right, cool. So hopefully that is just a nice review of what matter is. All right, so now what builds matter? So atoms are the most basic unit of matter. Hopefully you guys remember that. Basic unit of matter are atoms. And atoms are composed of subatomic particles. So at first it was thought that atoms build up matter, and then it was discovered that these subatomic particles build matter, build up atoms. All right, so let's do the follow along here. What is the most basic unit of matter? What builds matter? These are atoms. Okay, and then the 3 subatomic particles. I know everybody's heard of these before. We've got protons, neutrons, and electrons. And where are they composed in the atom? So the protons and the neutrons are in the nucleus, and protons are positively charged for P, and the neutrons are neutrally charged, so there's no charge on them, and those are in the nucleus. Okay, so dense kind of center of the atom. And then the electrons are negatively charged, and they flow all around here in the orbit, right? So they're kind of like flying around. And you can say that they're kind of kept in place because of the attraction from the positive nucleus and then the electrons, which are negatively charged. That's what keeps them into place. Okay, so those are our 3 subatomic particles. So let's go ahead and fill out our follow along for that. So we've got our 3 subatomic particles. We've got protons, we've got electrons, and we've got neutrons. All right, and then location in the atom, these are going to be in the nucleus, these are going to be in the orbit. I'll just say orbital shells, and we'll talk about what those are here, and then nucleus. And then the electrical charge here for the protons are going to be positively charged, electrons are going to be negatively charged, and then neutrons are neutral. No charge. Okay, cool. All right, so then we're going to go through this quite a bit today, the periodic table of elements and how this is organized and how we can extract information from this. So you're going to have the periodic table for you for any kind of quiz or exam. You're really going to have to be able to like get very familiarized with this and be able to extract information off of the periodic table. So atoms are collectively like listed or organized in the periodic table of elements. And what an element is a substance that can't be broken down any further. So it's like the most basic units of matter are these elements. And atoms make up elements. So for example, like we've got carbon, nitrogen, oxygen, fluorine, right? Hydrogen, etc. Those are all elements. They can't be broken down. Those are the basic ones. But you have atoms of an element. So for example, like the way I kind of like to think about this is like ice cream flavors, right? It's like a good analogy. So let's say that like hydrogen is a type of ice cream and carbon's a type of ice cream and nitrogen's a type of ice cream, etc., right? You can have, so those are all elements, right? Those are all like, you can't break down, for example, chocolate ice cream or vanilla ice cream or strawberry ice cream. But an atom or atoms are what make up the elements. So for example, you can have like scoops of ice cream within that bowl. So let's say that you're talking about like hydrogen ice cream. Hydrogen ice cream is that element, but the atoms make up that ice cream. So the scoops of ice cream would be the type of atoms, right? So you'd have scoops of hydrogen atoms that make up the hydrogen elements. And then you can mix things, right? You can make like chocolate, vanilla, and strawberry ice cream by taking atoms of all those different elements and putting them in a bowl. And that's how we end up getting molecules. Molecules are just combinations of these atoms. Okay, so that's what the difference is between an atom and an element. So an element, we'll say, element are the most basic units of matter, and they can't be broken down. And atoms make up elements. So you could have like you can have the element of hydrogen, but you can have multiple atoms making up that element, right? So that's how the best way to think about it. All right, so now let's look at how we're going to start extracting information from the periodic table. All right, so what are all these numbers, right? When we look at hydrogen here, what is hydrogen? It says 1 and 1. And what is oxygen? It says 8 and 16. So what are all these numbers? Okay, so the numbers on the periodic table will give us specific information. So what is an atom's atomic number? What information does this tell us? So atomic number is the number of protons in an atom's nucleus. So it's the number of protons, okay? But if we think about it, if an atom is neutral, like let's say that we just are writing out an atom like this, just hydrogen, right? It doesn't have the plus or it doesn't have the minus, which I'm sure you guys have seen before. So that would tell you that the atom is neutral. So if an atom is neutral, it means it has no charge, right? It means that it's gonna obviously have to have the same plus and the same minus numbers, right? And so for example, if you're talking about an atom that is neutral and we're talking about the atomic number as the number of protons, that would have to tell you that the number of protons equal the number of electrons, because electrons are negatively charged if it's neutral, right? So in this case, it would also be the number of electrons. All right, so that is what the atomic number is. So the atomic number is the number of protons in an atom's nucleus. And it also tells us the number of electrons if the atom is neutral. Okay, so let's look at like the most basic example here. So hydrogen, actually I'm going to pull up something here real quick. I should have pulled this up already. Periodic table of elements. Just because the ones that I have on my PowerPoint are kind of small, so let's see if we can find a better one here. Yes, okay, so look at this one. All right, so for example, then this is not showing us an atomic mass. Nope, this is not going to work. I need atomic mass. There we go. Okay, cool. All right, so let's say that we're talking about hydrogen. The smaller number on all of these are going to be the atomic number, right? This top number. Sometimes you'll see it inverted, but like on some, not necessarily on the periodic table, but sometimes when they'll give examples of it, like they'll flip the atomic number and the atomic mass. So sometimes you'll see that, but you always want to see the atomic number as the smaller number. So for example, like 8, 16, 7, 14, the atomic number is this one. Okay, so let's say that we're looking at hydrogen. Hydrogen's atomic number is 1. So this would tell us that if hydrogen's atomic number is, if we go back over here, we'll draw this out, let's say, talking about hydrogen. Okay, so let's make our hydrogen molecule, or hydrogen atom, excuse me, right here. And that would tell us if its atomic number is 1, it tells us that we have 1 proton in the center, in the nucleus. Hydrogen actually does not have any neutrons because its atomic number is only 1, right? So it would have to have at least an atomic number of 2 if it had a neutron, because we're going to talk about what atomic mass is in a second. So the atomic number is just 1, which means if you're just looking at H, it doesn't have any plus or minus, that would also mean it has 1 electron. Okay, so that's what we're saying. In a neutral state, hydrogen, for example, has 1 proton, has 1 electron. Okay, now what about if we start seeing something like this, H plus, H positive, H plus? That is something called an ion that we're going to look at here in a little bit, but that means that this is positively charged. This is an ion, it's positively charged, which means that it does not have the same number of protons and electrons. So H plus is actually just a proton. It's a hydrogen with just a proton. It's taken off the electron. So this is an ion. It somehow lost its electron. Okay, so that's what we're going to look at very shortly here when we start talking about ions. All right, so that's our atomic number. So for example, let's do carbon. So carbon is our example here. Carbon's atomic number is 6. So what does that tell us? So we see here 6 on our periodic table. So carbon's atomic number is 6. That tells us the number of protons is 6. That also tells us the number of electrons are 6. Okay, cool. All right, so now what about the atomic mass? So the atomic mass is the larger number on the periodic table. So that's these, right, the larger one. So hydrogen is 1, carbon is 12, nitrogen 14, oxygen is 16. That's the larger number. And what the atomic mass tells us, it's the number of protons and neutrons in the nucleus. So protons and neutrons in the nucleus. And so we say number, but mass is actually the mass of those, right? It's like the mass of the protons and the neutrons. But what's interesting is here, the mass of protons and neutrons both equal 1 Dalton. That's the unit of measurement for mass. So that's why we only say that the mass takes in effect. Like, why aren't we taking in the mass of the electrons? Because the mass of an electron is negligible. It's like 1 over 1840 of a Dalton. So it doesn't have a lot of mass, so that's why we just don't even include it. So when we're talking about mass, we're just saying the mass of the protons and neutrons. But since this ratio is 1, right, it's 1 Dalton, a lot of people just kind of go and they think of it as it's the number of protons and neutrons in the nucleus, right? As opposed to saying, okay, the mass is 1 Dalton of protons and neutrons. Since it's a 1-to-1 ratio, right, 1 Dalton to 1 particle, we're just going to say it's the number of protons and neutrons. Okay, so that's kind of where you hear that thing going on a lot. All right, so if we go here, what is the atomic mass? What information does this tell us? So the atomic mass is we'll say the mass, or simply the number of protons plus neutrons. Electrons, we'll say, are not included because their mass is negligible. Okay. All right, so then let's do our example here. We've got oxygen. So what did we say oxygen's atomic mass is? Oxygen's atomic number, hopefully you can see that, is 16. So if it says 15.99, we want to round up. So that is 16. Okay, so that tells us that wrong space. Atomic mass is 16, and the atomic number is 8. So you can see that atomic number is 8, and it'll probably be helpful. I think I have a periodic table posted on Canvas, but it would be helpful as we're going through this for you guys to have. If we were in class, I would have given you a periodic table, so it will definitely be helpful for you to have a periodic table on hand while we're doing that. So that's 8. Okay, so then now our number of protons we get from our atomic number, so we know that that's 8. And if this oxygen is neutral, it just says O, right? Just like this, there's no plus or minus, and we know that the electrons also have to be 8. So how do we get the number of neutrons? Well, we know that the mass is the number of protons and neutrons. Okay, so we do 16. 16 minus 8 would equals 8. Okay, do you see how I did that? Because we know that the atomic mass refers to protons plus neutrons. So if our atomic mass is 8, and then we can subtract out the number of protons that we have, that's going to leave us with 8 neutrons. Okay, so or if we just kind of work backwards, 8 neutrons plus 8 protons will give us 16 atomic mass, and because we know that's protons and neutrons. So that's how we'll do that. Okay, so definitely, if that did not make sense, take a look at that a couple more times because that's going to be a really important concept here. Okay, all right, so now let's do a couple practice problems, and then we'll fill out our table here, and then we'll do a couple practice problems. So we said already that the atomic number is the number of protons, and then also the number of electrons in a neutral atom. For example, carbon equals 6. Okay, and then the atomic mass is the number of protons plus neutrons. And so carbon equals 12. Okay. All right, so I've got a couple practice problems here. So titanium has an atomic number of 22. How many protons, neutrons, and electrons are in an isotope of titanium with a mass number of 48? So we're looking at 22, and we are looking at 48. Okay, so what is this going to tell us? So it's going to tell us first, if we have the atomic number, we know that the proton number has to be 22, right? So we can eliminate B, C, and D. So it's either going to be A or E. Protons are 22. And if this is neutral, titanium, we're not saying any plus or minus, we're not saying it's an ion, it's just a regular atom of titanium. That means that the electrons also have to equal 22. So electrons are going to equal 22. And then how do we figure out the neutrons? Well, remember our atomic mass, which we're saying is 48, is protons plus neutrons. So if we just take 48 minus 22, right, which are a number of protons, that'll give us our remaining neutrons. So that would be 26. So our answer here should be A. So protons and electrons are both 22, and our neutrons are 26. Okay, so it's really simple. Hopefully that should be easy to understand. So we've got one other application question here. So what are the number of electrons, protons, and neutrons of phosphorus? P. Okay, so P is going to have, obviously, if the atomic number is 15, that means our protons equal 15. It means that our electrons are going to equal 15, and then our neutrons are going to have to be 16 because we're just taking 31 minus 15, right? Because remember, 31 is our atomic mass, and that tells us our protons plus neutrons. And if we know that our protons are 15, that we extracted from the atomic number, we just take 31 minus 15, and then our neutrons equal 16. Okay, so hopefully that makes sense. How many electrons are present in the valence shell? So we haven't talked about that yet, but I guess I can show you guys that really quickly. So our valence shell is going to be the outer shell of our atom. Our valence shell is the outer shell of our atom. So electrons are arranged in shells in a very specific way. So if we're talking about P, we've got our first shell, which can only hold 2 electrons, like this. And then we have our next shell. And actually, let's write this out here. So we're talking about, these are our electron shells, because in the nucleus here are going to be our protons and neutrons. So P, we already said, has 15 electrons. 15 electrons. So we've got 2 in the first shell. There can be 8 in the second shell. So 1, 2, 3, 4, 5, 6, 7, 8. So how many is that total? That's 8 plus 2 is 10, 11, 12, 13, 14, 15. So it has 5 in the valence shell. So hopefully that makes sense. And I got that written over here, 5. And then which is it going to react most similar to? So how it reacts most similar is going to be whatever else is going to have a valence of 5. So when we look at the periodic table, we're going to talk about this soon, but atoms are arranged on the periodic table based on their valence electron. So these numbers here, 1, 2, 3, 4, 5, 6, 7, 8. Do we see that, right? 1A, 2A, 3A, 4A, 5A, 6, 7, 8, etc. That indicates the number of valence electrons, or electrons in the outer shell. So we said that phosphorus has 5, and that's what we just showed you, right? And that is in this column 5, right? So which atom is going to react most similar? Something obviously that has the same number of valence electrons, because the number of valence electrons you're going to see here shortly is how atoms interact with other atoms to form molecules, because atoms want to have a full valence shell. They don't like to have, for example, like that third shell that phosphorus has that we just showed, it only has 5 electrons in there. It doesn't want to have 5. It wants to have 8. It wants to maximize all of those spaces. So any atom that has the same amount of valence is going to have that same properties. It's going to exhibit the same kind of interactions with other atoms. So phosphorus is going to act most similar here, in our case, to nitrogen. So that of all of these other ones, so it's going to react most similar to nitrogen. Okay. Nitrogen. And we can even, if you'd like, just because we're getting started with all this, let's draw out nitrogen. So nitrogen's atomic number is 7. Okay, so when we draw out nitrogen here, nitrogen is able to put 2 in its first shell, and then in its next shell, 2, 3, working so well on the first one, 2, 3, 4, 2, 3, 4, 5, 6, 7. Okay, so you see how I did that? 1, 2, 3, 4, 5, 6, 7. And that would give it 5 in its outer shell. 1, 2, 3, 4, 5, which was the same as we had with phosphorus. 1, 2, 3, 4, 5. So that's why they're going to react most similar to phosphorus. All right, so that's jumping ahead a little bit, but it's okay because we're going to get there here in a second. All right, so then before we get to all those orbitals here, which is coming up in a slide or two here, one other thing about the neutrons, like the atomic masses. So what are isotopes? So isotopes are atoms of an element that have different atomic masses. And we said that an atomic mass is the number of protons plus neutrons. So what the atomic mass is and how these different atoms become isotopes, they have different atomic masses because they have different number of neutrons. So most elements and atoms in nature actually have a mix of isotopes. They'll exist as isotopes. What you see on the periodic table are the most common isotopes, the ones that are most prevalent in the environment. So for example, carbon we know to exist in at least 3 different types of isotopes: carbon-12, carbon-13, and carbon-14. So what you see on the periodic table is C12, because that is the isotope that exists most in nature. So they say that 99.9% of the isotopes or atoms out there of carbon are in the C12 configuration. And so C12 is 6 neutrons, 6 protons, and 6 electrons. We determined that before, right? Because remember, carbon has an atomic number of 6, which means it has 6 protons and 6 electrons. And then its atomic mass is 12. So that would add in 6 neutrons to the protons, right, to give us 12 atomic mass. So if you look here, how do we get C13? How do we get C14? Well, C13 has 7 neutrons, so it has 1 more than this, so it's C13. And then C14 has 1 other neutron in addition to that, so that's C14, and that would be 8 neutrons. Okay, and isotopes, you probably have heard of like radioactive isotopes. Isotopes are radioactive because they shed their nuclei, so they can give off their proton, they can give off their neutrons, and that is what radioactivity is. It's like when they shed, they decay their nuclei, and then if they decay their nuclei, they're losing those subatomic particles, so they can drop back down to C13, C14, or C12, for example. And that's why they're not stable. So that's why the majority of the isotope is going to be C12, because these guys here are not stable. So they'll decay those nuclei and they'll drop back down to C12. Okay, so that's what an isotope is. All right, so what is an isotope? Isotopes are atoms of an element that have different atomic masses. Because they have different number of neutrons. Okay, so for example, we had C12, C13, and C14. Okay, cool. And then you have that, and you can see that they have different number of neutrons within their nuclei. Okay, so I'm going to skip this. I'm not going to test you guys on this. I'm just going to skip this about the radioactive isotope. But radioactivity, just like real quick, I'll just make one note about it. Radioactive isotopes are used, for example, for like carbon dating. Carbon dating I had on this slide here. So the half-life, the decay of the radioactive isotopes is measured by half-life. And this is the time needed to decay half of the atoms of a sample. So if you have, for example, you know, C14 like has a half-life of 5,600 years. So for example, if you have 1 gram of C14 in 5,600 years, you would assume that you would have half a gram, right? Because it's going to take, that's the amount of time that it takes to decay half the atoms in the sample. So if we have 1 gram and we go through 1 half-life of 5,600 years, we're going to have a half a gram. And then in 200 years, we're going to have a quarter of a gram, right? Because that half a gram is going to degrade to a quarter of a gram. So that's how we do this. So radioactive isotopes have many useful applications. So for example, carbon dating, I threw up here, which is an interesting example. So carbon dating and how they age different things on the planet is that they have this known ratio of C12 to C14 in the environment, right? And then what happens is, because they know, like we said, that C12 is going to be the majority of the isotope out there. So it's the rate, they know the ratio of the C14 to C12. And it's the same in all organisms and in all life. So the radioactivity of C14, and this is what I jotted down here, it's going to start to decay over time, right? But it's not going to be replaced. But the C12 levels are always going to remain constant because that one's not decaying. So if you just compare the two values from what they originally were, C14 to C12, you'll know how much has decayed and how long that sample has been decaying. And so that's how they can actually do like fossil dating and things like that. So it's a really cool example. Okay, and then I had an example over here of which of the following best describes the relationship between the atoms below. So we have hydrogen 1 and 1, which is our normal isotope, and now we're looking at H1 and 3. So it has 2 neutrons right in here. This is now 3 for the atomic mass. So obviously this is going to have to be isotopes because that's the only thing that we've talked about. We haven't talked about isomers or polymers or any of these other answers yet. So that would be an isotope. Okay. All right, so now let's look at how these atoms arrange electrons in the shells, right? This is like starting to get into the topics of how we make molecules and all that. All right, so electrons are going to be arranged in an atom in orbitals. So an orbital is where the electrons hang out, and they can either be spherical or dumbbell shaped, and they're going to hold a max of 2 electrons. Okay, so the orbitals are where the electrons hang out, and they can hold a max of 2 electrons, and they can either be spherical or dumbbell shaped. Okay, now the orbitals are arranged in shells. All right, and then there's various shells that make up an atom. So K is going to be the shell that's closest to the nucleus, and K only contains 1 orbital. So that's why we say that first shell closest to the nucleus can only hold 2 electrons. Okay, the next shell beyond K is called L, and L has 4 orbitals, so it can hold 8 electrons. And then the shell beyond that, M, the shell beyond that, N, they also each have 4 orbitals, so they can hold 8 electrons and 8 electrons. The max that we'll do in this course is probably up to level M, okay? And then I have like the names of these. So for example, this first shell, the orbital is called 1s. The orbitals of the next shell are called 2s, and then 2p, or we've got 3p, sorry, x, y, z. I'm not sure I'm going to have us really go through that whole shell configuration for this class. If you guys go on and take a chemistry class, you'll move more into that. But for us, it's not as important. I just want you to be able to understand that the first shell is going to hold 2 electrons, second shell can hold 8 because it has 4 orbitals, and third can hold 8 because it has the 4 orbitals. Okay, so let's go ahead, take a minute, choose an atom on the periodic table, and illustrate its electron configuration. So if you want to pause for 1 second and try that, and then I'll do an example. I just want to see, get you guys, if we were in class, we would be doing this quite a bit, just giving you the hands-on experience to drawing out atoms in the electron configuration. So I will do an example. What about if we choose something? Yeah, don't do anything crazy down here because we won't get that far. Let's do, what about if we do oxygen? What did we do already? We did carbon. We didn't do oxygen yet, did we? Okay, what about if we do fluorine? So fluorine's atomic number. Now we do something crazy. I don't know, this thing doesn't work very well. So fluorine, what did we say fluorine's atomic number is? Fluorine's atomic number is 9. So remember, you're using the atomic number and not the atomic mass when we do this, because the atomic number is what tells us the number of protons, but also tells us the number of electrons if it's neutral. So this atomic mass is protons plus neutrons, so we don't want to use that number. We want to use the smaller number. So fluorine's atomic number is 9. Okay, so if we do fluorine like this, and we said that we can fit 2 in the first shell. So 1, 2, 3, 4, 5, 6, 7, 8. And let me actually go back because I want to show you we should not be doing it like this. I was doing it like that for simplicity, but I don't want to have us do it like that because I want to show you how they actually really fill up there. Okay, so we said that fluorine's atomic number is 9. So we go like this. So we have 1, 2 in the first shell, and then the way the second shell fills up, it actually goes like this. We actually do 1 for each orbital at a time. I didn't want to go ahead and I just do it shorthand like that. But the better way to do this is because actually how they fill up is they'll fill up each orbital 1 at a time. So they'll go 1, 2, 3, 4, and then 1, 2, 3, like this. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we've got 1 extra that we're missing right over there. So at first I just drew like 2, 2, 2, and then I put the 1 over here, which is correct, but I want you guys to get into the habit of filling up the orbitals 1 at a time, because that's how that happens. So it'll go like 1, 2, 3, 4, and then it'll go back around. And that's just to maximize the space around all the orbitals, so they all will at least get 1 if possible, and then they'll kind of backtrack and go fill up the next ones. All right, so this is fluorine. So fluorine's atomic number we said is 9, so it's 2 in the first shell, and then 7 in the second shell, and its valence is just going to have 1 extra, right? It's 1 missing 1. So if we went back and looked at the periodic table, that's what we got here. We can see fluorine is in column 7, right? Because it has 7 in its valence shell. Okay, so hopefully you guys had an easy time choosing an atom and illustrating its electron configuration. Okay, so we've got a couple questions here, and then we'll go do our follow-along guide. So an atom of oxygen has the atomic number of 8. How many electrons are in the first, second, and third shells, respectively? So oxygen is going to be equals. Sometimes it lets me write more than 1, sometimes it doesn't. I don't know why. So oxygen is 8. So it has 2 in the first shell, 2, 3, 4, 5, 6, 7, 8. So you see how I did that? Correct the sign, going one around each time and then filling up the other 2. So this one is going to have a valence of 1, 2, 3, 4, 5, 6. So 6 in its outer shell, and it's missing 2 more that it wants to have, wants to maximize. So our answer here is going to be B. So 2, 6, and 0. So 0 is just none in the complete outer shell. We only went to that second shell in oxygen. And then that's what I showed you here. that our atomic number, our atomic mass, and they're going to be arranged in columns based on their valence electrons. Okay, so it's easy, right? Hopefully this is all a review. What do elements then with the atomic number 1, 3, and 11 all have in common? So if you look here, atomic numbers 1, 3, and 11, we see here, they all have a valence of 1 because they're in column 1. So they're all going to have the same number of valence electrons, and they're going to exhibit similar properties. And what that properties means, and we're going to talk about that now, is how they interact with other atoms to form molecules. Because even with the example that I showed you with oxygen, oxygen is missing 2 electrons that it could potentially have. Because remember, the valence, they want to have a valence of 8, right? They want to maximize all those orbitals. So this is how we start to get other atoms bonding to atoms to fill their valence electrons to maximize that. And that's how we get molecules forming. So for example, oxygen, we're going to look at quite a bit. What about if we take hydrogen? So hydrogen, we looked at hydrogens. So hydrogen's atomic number is 1, which means that it only has 1 electron in its valence shell, right? But it wants to have 2 because it has only 1 shell. And remember, we said in that first shell, it has 1 orbital, and that orbital can hold 2 electrons. So hydrogen is going to come in here, and it's going to want to share that 1 electron it has with the one missing one from oxygen. So hydrogen is going to come over there, and then this other hydrogen will come over here, share that 1 electron with this electron over there, and then everybody's happy. And so this is the example that we have here is H2O. So everybody's happy. So hydrogen has 2, right? And it's happy because it had 1 electron, and then it maximized that by taking the other, sharing the other electron with oxygen and filling up that 1 orbital in that 1 shell. And then oxygen had 1, 2 in its first shell, and then 3, 4, 5, 6, 7, 8, right? Because its atomic number was 8, so it had the 6 in its outer shell, needed 2 more, shared the other 2 here with the hydrogen, and it's all happy because now it has 1, 2, 3, 4, 5, 6, 7, 8. So now we're all good. All right, so then let's go ahead before we start looking at some other concepts here. Let's fill out our follow-along guide. So what are electron orbitals? How many electrons are held in orbitals? So electron orbitals are where electrons are found in an atom, and then each orbital can hold 2 electrons. Okay, and then what are electron shells? Electron shells are where orbitals are arranged in, and then how many orbitals are contained in each of the shell below, and then how many electrons fit into each shell. Okay, so then the electron shells are where the orbital are arranged in, and they have different numbers of orbitals. The electron shells. So for example, first shell has 1 orbital, which is 2 electrons, and second shell has 4 orbitals, which is 8 electrons, and third shell has 4 orbitals, which is also 8 electrons. All right, cool. So this is fun, right? So how many electrons, or how many electron orbitals are contained in each of the shells below, and then how many electrons can fit in each one. Okay, so remember we said that K is our closest one to the nucleus. So that has number of orbitals, it just has 1, so it can only hold 2 electrons. L, M, and N. This is the second shell, third shell, and fourth shell, respectively. And these all have 4 orbitals. And remember, each orbital can hold 2 electrons, so this can hold 8 electrons, 8 electrons, and 8 electrons. Okay, so definitely highlight this. Make sure you guys understand that really well, because we're going to do a lot with this electron configuration throughout the whole class. All right, choose an atom on the periodic table, illustrate its electron configuration. Hopefully you took a minute to do that. I did the oxygen example. And then let's go on to some other concepts here now. Okay, so we've already kind of jumped ahead and we've done a little bit of this, so this should hopefully start to be making sense here. So a 19th century Russian chemist, Dmitry Mendeleev, he's the one who organized the periodic table. And like we said, he already arranged them in groupings by their valence electrons, and that's where we see them in those columns. And then the valence, remember, are the electrons in the outermost shell. So that's what you've seen a couple of these already. So this is how they're organized in these columns, and the 1A, 2A, 3, 4, 5, 6, 7, 8 are the number of valence electrons. So we've already seen this a little bit, right? So valence is outer. So we got hydrogen, we said had 1 in its valence shell. We saw carbon had 4 in its valence shell because its atomic number is 6, so it can fit 2 in the first shell and 4 in the second shell. We illustrated oxygen, which had 2 in its first shell and 6 in its valence shell because it had an atomic number of 8. I also showed fluorine. Fluorine's atomic number is 9, so it had 2 in the first shell and then 7 in its outer shell. So that's what we're looking at, valence, okay? So our first thing here on our follow-along guide asks, what is atomic valence? And so valence is the outer shell. So for example, carbon valence equals 4, oxygen equals 6, we said fluorine equals 7, and then we can see this info by the column number. Okay, so that's what valence is. All right, so what is the octet rule? So I've mentioned this a little bit already. The octet rule is the fact that an atom wants to have a full valence shell. And called the octet rule because most of the atoms that we work with are going to want to have 8 in their valence shell because they all have that second valence. There's only one atom, well actually 2, that don't follow this that are exceptions to this rule. One is hydrogen, because hydrogen's atomic number is only 1. So it can only maximize and ever have 2 because it's only going to have that first shell, right? K. It's never going to be able to get all those electrons to fill up a second shell. So even though it follows the rule of valence, it's not going to be the octet rule because octet indicates 8, but it will follow the valence that it wants to have 2. And helium's also an exception because helium already has a valence filled with 2. So it's something called like a noble gas. It's inert. It's non-reactive, which we'll get to here in a second. But both of them follow the rule in the fact that they want to be stable and they want to have the full valence. It's just not filling up 8. Okay, so that's what the octet rule is. So the octet rule is the fact that atoms want to have a full valence shell to be stable. Okay, and then this is 8 electrons for most atoms. And hydrogen and helium are exceptions. They still want a full shell, but full outer shell. But this will be 2 electrons because they only have the first shell. Okay, cool. And then chemical bonding, like we've already said too, is the fact that atoms will want to come together to fill up their valence shell. And that's what molecules are. So molecules are formed because atoms want to come together with other atoms to fill up their valence. So this was the example that I showed you up here, like with water, H2O. So why does water form? Well, because oxygen is missing electrons in its valence and it wants to get filled up, so it's happy. Because this is like before when we just had oxygen, we had the two hydrogens. These atoms are not happy, they're not stable because they don't have full shells. But when these simple atoms come together to form a molecule, for example, water, now everybody's happy because oxygen has 8 in its valence and the hydrogen has 2 in its valence. So it's now a happy, happy molecule. Okay, so that's the whole purpose of chemical bonding between atoms, enables them to complete their valence shell. All right, so I mentioned helium. I said helium is kind of an exception to this because helium is considered a noble gas. It's inert, which means it's non-reactive because it has a full valence shell. So every atom that is in that column 8, they all have a valence shell because think about it, and you even have it like drawn out like this, which is easier than me doing this little tool. Helium only has its first shell. This is actually a really, really good slide, this one, for you guys to take a look at. Helium here has a first shell, so it has 2 filled up already. Neon, which is the next one, neon's atomic number is 10, so it has 2 in the first shell and then 8 in the second shell, which is filled. Argon's atomic number is 18, so it has 2 in the first shell, 8 in the next shell, and then 8 in the next shell. So everything's all filled up. So these are complete. They're non-reactive. They can't associate with other atoms because there's no space, right? They have no space to share atoms or share electrons or donate electrons or anything. They are inert. They are non-reactive. So that's everything that you see here, all in column 8. Those are all our noble gases. All right, so with that information, let's go ahead and we'll do our follow along guide for that one. Okay, so noble gas, and I got this little thing here for you to cheat from. So our noble gases here are going to be helium, neon, argon, krypton, xenon, and radon. All right, and then the number of electrons in the valence shell are going to be 2 for helium because it only has that first shell, and then 8, 8, 8. Oop. 8 and 8. And then is this reactive with other molecules? No. And that would be the same all the way down here. None of these are going to be reactive. Oh, never mind. No. Okay, cool. All right, and then which of the following atoms would you least expect to see forming molecules? That would obviously have to be helium because helium is one of the inert noble gases. All right, so now moving into other concepts. So what is the term of electronegativity? So electronegativity has to do with how many valence electrons an atom has. So an atom that has way more electrons in its valence is obviously going to be more electronegative, right? Because it has more electrical or negative electrical charge. So think about something like, let's go back to this one because this is a really good slide of this. Like let's say that we're looking at something like fluorine, right? Look at how many electrons fluorine has in its valence. 1, 2, 3, 4, 5, 6, 7. So fluorine is way more electronegative. It has way more electronegative charges as opposed to something like lithium. Look at lithium. Lithium only has 1 in its valence, so it doesn't have a lot of negative electrical charge. So something like lithium is not very electronegative. Okay, so that's what electronegative means. It means it has a lot of negative charges. Now, electronegativity also has to do with how aggressive an atom is. So an atom that is more electronegative is going to have a greater pull of electrons on it in itself to pull other electrons towards itself. So it's more aggressive because think about it. An atom that we're sitting here like fluorine only needs 1 more electron to fill its valence shell, right? Because right now it has 1, 2, 3, 4, 5, 6, 7. So it only needs 1 more electron. So it's super aggressive because it's like, hey, I only need 1 to fill my shell. So it's going to pull electrons from other atoms. So that's what it means by electronegative. Versus lithium. Lithium, for example, or sodium, even hydrogen. Well, hydrogen only needs one, so it's kind of an exception. But if we're looking at like lithium or sodium, sodium has one in its valence, lithium has one in its valence. So it's like, heck, there's no way I'm going to get 7 more electrons here to fill my valence shell. So it's like not electronegative at all, because it's like, hey, I'll just give away this 1 electron, and then I'll expose my undershell, my shell below it, and I'll be perfectly happy because that's full and that's stable, right? So these atoms on this side of the periodic table with very low valence number of electrons, right? They're low electrons in their outer shell, and they're not very electronegative. But atoms over here are very high in electronegativity because they've got a lot of electrons in their outer shell. They're very, very aggressive. Okay, so that's what that means. That's what electronegativity is. So electronegativity is going to be highest in atoms that have a lot of valence electrons. So example 7, like fluorine, and then ones that do not have a lot are not going to be very electronegative. Okay, so that's what electronegativity is. So what is electronegativity? List an atom as an example with low and high. Okay, so electronegativity is the amount of electrons which is negative charge in the valence shell and atoms with more electrons in their valence are more electronegative because want to fill that outer shell. All right, so let's an example of an atom with a high electronegativity and low electronegativity. So we said a high electronegativity, for example, would be fluorine. Fluorine, because it has 7 valence electrons, and then an atom that has low electronegativity, we could say, for example, is sodium, Na, only has 1 valence electron. Okay, so hopefully that makes sense. Remember that atoms that have a lot of electrons in their valence are going to be more electronegative because they have all that negative electrical energy, and because they have the desire to fill that valence shell. So they're going to be more aggressive. They're going to pull the electrons of other atoms towards themselves. Atoms that do not have a lot of those negative electrons in their valence are going to say, hey, just take them because I want to fill my lower shell. So they're going to be less aggressive. They're not going to be as electronegative. Okay, so that's an example of those two. So like, how do we work now with electronegativity? So if we look here, the periodic table, on the periodic table, the trend of electronegativity is going to be up and to the right. So you can see here, fluorine has an electronegativity value of 4, which is our highest. Fluorine is going to be pretty much our most electronegative atom that we know. When we're talking about up and to the right, remember we're not including the noble gases in this column 8, right? Because those guys here are already filled. They're inert. They have full valence shells, so they can't take any more. Even though, yes, they do have a lot of electrons in their valence shell, and you would consider them to be electronegative because they've got a lot of negative charge, they don't have the desire to pull electrons towards themselves because they don't have any room, right? They're already complete. So when we're looking at up and to the right, we're talking about like fluorine being our max. It's going to be our highest one. And if we think about it, all of these here in this column, 7, they all have a valence of 7. So they're all really, really electronegative. Chlorine, bromine, etc. Oxygen is also relatively electronegative because it only needs 2 more, right? Nitrogen needs 3 more. Carbon needs 4 more. So it's just going to get less and less as we go this side, or more and more electronegative as we go up and to the right. Okay, so that's like the trend that we're looking at here. And then there's also an electronegativity value chart, which I will give you also on a quiz or exam if you have to extract information from here. So these numbers all represent the relative electronegativity. So we said fluorine is close to a 4, oxygen's Electronegativity is 3.44, nitrogen is 3.04, carbon is 2.55, etc. So those are the electronegativity values. Now, the electronegativity values are how we can form bonds and how we'll determine what kind of bond is going to form between atoms. Okay, so this is going to be like bringing us into the next part of this chapter, and this is really important. So how electrons or their electronegativity between different atoms is how bonds are going to form between atoms. So if we look at this next chart, this is the bond type chart based on the difference in electronegativity. Okay, so if we think about something that two atoms that come together that have the same kind of electronegativity, right? They're going to form more of a covalent bond. So we're going to talk about what these bonds are in a second. A covalent bond is when the electrons are shared between an atom. And I haven't really shown you that yet. I only showed you like the bonds between water, oxygen and hydrogen. But a covalent bond is where the atoms will share electrons between the atoms that are involved in a molecule. And there's various degrees of covalent bonds. There's nonpolar and polar, and we'll talk about what that means here in a second. And then there's also ionic bonds. And ionic bonds are when the electrons are not shared. It's when electrons are either like stolen, taken from an atom, or given to an atom, and it's not an equal sharing. So that is where we form ions. And if you remember back from one of the first slides we did today, we talked about an ion is an atom that has a different number of protons and electrons, right? And so we don't have that neutral charge anymore. So let's say that an electron was taken off of an atom, that atom is going to be more positively charged. Or let's say that an electron was added to an atom, that atom is going to be more negatively charged, right? Because we're now talking about the difference between the positive protons in the nucleus and the electrons or the negative electrons in the orbit. Okay, so when that number differs, we don't have a neutral atom anymore. Okay, so we can use electronegativity to help us to see what kind of bond is going to form. So we've got this an electronegativity chart, and then this is also showing you another one. So how do we do this? So let's take a look at how we're going to form some electronegativity bonds, and then we'll look at what these bonds actually mean. So let's look here, and I'll show you how this all works. Okay, so we said that electronegativity of atoms influences the type of bonds that are created between atoms when atoms bond together. So we're going to complete the molecules in the table below, and we're going to use this chart. Okay, so let's say, let's go back over here. This is really easy once you see how this all works. Okay, so let's say that we're talking about a molecule of hydrogen gas, H2. So how this works here, and let me actually draw this out because this is one that I didn't show you before. Let's go up here to do this one. Once I get this tool working. Okay, so H does not like me today. H, nope. Try one more time. H. Okay, good. Thank you. H and H. Okay, so hydrogen's atomic number is 1. Hopefully remember that. And then this one is also going to be 1. So hydrogen's atomic number is 1. We know that based on the periodic table H1. So hydrogen only needs one more to fill its valence shell, right? Because it only has one orbital because it's only in the first shell. So what happens is hydrogen will basically share these two electrons. Get rid of that little guy. And it's sharing these two electrons. So anytime you see this, like the lines like this, it looks like an equal. This means that this is each one of these is an electron bond. Okay, and so this is one pair of electron, this is one electron, and this is one electron. So this is a pair of electrons, 2 electrons. So now this is happy and this is happy because they are never going to want to fill that second shell of 8 electrons because there's no way they're going to get 8 more electrons. So hydrogen right here is really happy as H2, the molecule. So this is H2 hydrogen gas, happy. Okay, so this is a type of covalent bond, just equal sharing. All right. I'm going to show you what an ionic bond is. I'm just going to jump ahead real quick and show you an example of an ionic bond. So let's look at sodium chloride. Sodium chloride, or how we form salt, is actually formed from an ionic bond. So where you just saw with hydrogen, hydrogen was really nice and happy, covalent bond, it would just share those 2 electrons. With sodium chloride is an ionic bond because look at what's going on. Ionic bonds form when you have 2 atoms that have very different electronegativities. When we saw hydrogen, H and H, they have the same electronegativity, so they are not aggressive. Neither of them are like overly aggressive and like stealing or donating electrons. So it's just a nice, easy covalent bond. An ionic bond, on the other hand, involves atoms that have different electronegativities. So, for example, sodium and chlorine. When we look back at the periodic table, chlorine is in here in this column, which is 7 valence electrons. So remember, super electronegative, super aggressive, because chlorine's only missing 1 in its valence shell. Now, if we looked at sodium, sodium only has 1 in its valence shell, so it's like, heck, take that electron, I don't care, because I'm going to expose my lower shell and be all happy. So this is also not aggressive at all, it's not very electronegative. So when you have atoms that are not electronegative and very electronegative coming together, they form an ionic bond because ions are formed, because there's like a theft and there's a loss and a gain of an electron. So chlorine, super electronegative, basically outright steals that electron from sodium, and it now becomes Cl minus 1. Chlorine minus 1. It's minus 1 now because it has an extra electron that it didn't have before, so it's more negatively charged compared to the protons in the nucleus. Okay, so it's all happy now because it has that 1 valence shell, 1 extra electron in its valence shell. And then sodium was like, oh, I don't care, take it, because now it exposes its lower shell and it's happy. So both of them are happy in this arrangement, but now sodium becomes Na plus 1 because it's deficient, it's minus an electron now because it gave it to chlorine. So this is an ionic bond because 2 ions are formed. An ion, remember, is an atom that has a different number of electrons and protons, so it's charged. It's not a neutral atom. So chlorine is minus 1 and sodium is plus 1. And when they come together, that plus and minus attract, and this is what we get. Na plus together with Cl minus, this is an ionic bond because we're forming the 2 ions and they're coming together, the attraction of the ions. Okay, so with that in mind, let's go ahead and we're going to we're going to do some examples here. The bonds, showing you the bond types and what kind of atoms are involved in that. All right, so how we're going to do this is H2, for example. The atoms that are involved in this molecule are H and H. That's what's involved. The electronegativity values of the atoms in the molecule. So H equals 2.2. So if we go back to here, H equals 2.2. So those are our electronegativity value. So do we see we got that? So the molecules that are involved are hydrogen, hydrogen. The electronegativity value of the atom is 2.2. So the difference would just be 2.2 minus 2.2 equals 0. See how we did that? Because this is 2.2 and this is 2.2, so 2.2 minus 2.2 is 0. So now if we look back at the bond created, if we're 0 to 0.39, we're non-polar covalent. So now we are non-polar covalent. So this is a complete equal sharing, and we'll look over what non-polar means in a minute, but that was an equal sharing I showed you like this, right? Versus the ionic bond, you'll see how we generate in a minute. Okay, so let's do another one. O2 and O2, the molecules that are involved are oxygen and oxygen. Let's look and see what oxygen's electronegative value is. Oxygen is 3.44. So oxygen equals 3.44. And we're just going to, again, 3.44 minus 3.44 for the 2 oxygens equals 0. And again, that is non-polar covalent. All right, so now what about if we do a molecule like CH4? CH4 looks something like this. We talked about how carbon's atomic number, if this works, C. Okay, so let's look here. Carbon's atomic number is 6, and it's in the column 4, which means it has 4 valence electrons because we fit 2 in the first shell and then 4 in the outer shell. So carbon is going to this is a molecule called methane, and carbon, oh, that's why, because I did a circle. I did the wrong line. Okay, so C, and then carbon is going to want to form all right, hopefully you guys can understand what I'm drawing there because that did not work very well. But carbon had 4 in its valence. So 1, 2, 3, 4, and hydrogen, remember, has 1 in its valence. So this molecule here is called CH4, methane, very common formed organic molecule. Carbon will easily pick up molecules or other atoms of hydrogen and make a covalent bond with them because each hydrogen just needs 1 and then carbon needs those 4 extra ones. Okay, so when we do this molecule on the periodic or on our electronegativity value, we have the molecules that are involved. We have 1 carbon and 4 hydrogens, okay? And our electronegativity values, if we look at hydrogen, remember, equals 2.2, and carbon equals 2.55, I believe. Carbon, that 2.55. So you see where I'm getting that? 2.55. So you go 2.55, and now because each of these bonds is going to be the same, right? We don't need to do this 4 times. We could just do one example of this, and then that will show us like what each of these type of bonds is, because this is going to be the same thing 4 different times. So you just have to do it one time. So we can just do 2.55 minus 2.2, and that is going to give us 0.3. All right, so 2.55 minus 2.22 gives us 0.3. And then if we look here, I don't know why these things keep forming now. Okay, so then 0.3 is also going to be still a nonpolar covalent bond. So nonpolar covalent. And we only had to do that one time. Okay, H2O, I'll let you guys go ahead and do that on your own. H2O, again, you'd have to do the difference between the carbon and the oxygen, or the oxygen and the hydrogen. CO2, I'll let you guys go ahead and do that one, and then let me show you, or actually let me show you this one because this is going to be polar covalent, and ionic. So this is going to be polar covalent. This is going to be polar covalent. And then this is going to be ionic. So let me show you an example of this one. So let's do H2O. So H2O, you're going to have 2 hydrogens and you're going to have 1 oxygen. And then hydrogen, we said, is 2.2, and oxygen is 3.44. I'm just getting that information from up there or the other chart. So we have on this case, we've got 3.44 minus 2.2 equals 1.2. So if you look at our chart here, 1.2 is going to be polar covalent. Okay, so polar covalent for that one. Now let's look at ionic bond. And so NaCl, we're going to have 1 Na, and 1 Cl. And then sodium is going to equal 0.93. And chlorine equals 3.16. And so if we do 3.16 minus 0.93, that's going to equal that's going to equal 2.23. And if we go here, 1.7 or greater is ionic. Okay, so that's how we're going to do that whole table. So hopefully that made sense just in how to figure out how to go ahead and do those, how we're going to go ahead and make those bonds, and then let's go ahead now and look at how we're going to look at what those bonds are, like what type of bonds those are forming right now. Okay, so that's this chart, that was the water one. All right, and so which of the following atoms is considered the most electronegative? If we look at our periodic table, we said fluorine, so that would be this answer here, fluorine. All right, and now let's go ahead and look at what all these different types of bonds are. Okay, so ions. What is an ion? So we've gotten through this a few times so far, so hopefully this is starting to make sense. So an ion, we said, is any atom that has a different positive to negative charge. An ion is when an atom will either gain or lose electrons in its valence, and then that is going to give it either a positive or a negative charge, because the positive protons in the nucleus now do not equal the negative electrons in the valence shell. Okay, and so that's what an ion is. It's created from the addition or removal of an electron. And so there's two types of ions we're going to look at. One are called cations. Cations are going to be a positive charge because they carry more protons in the nucleus than electrons in the valence. Okay, so they're going to be positively charged. A good example of a cation, and I'll show you here in a minute, is going to be like the sodium that I showed you before in the salt solution, right? Sodium becomes Na plus because it lost the electron in its valence shell. And then an anion is going to be negatively charged because it carries more electrons in its valence. So that's the difference between a cation and an anion. Okay, so let's go here. What are ions? And then fill in the table below, and then draw out the example of an ionic bond between NaCl. Why would this not be the best to build molecules and cells? So we'll talk about that in 1 second. So an ion, these are going to be atoms that have positive or negative charge because they have different numbers of protons plus 2 electrons. Negative. They are not neutral anymore. Okay, because remember on the periodic table, all of these atoms that we were originally looking at, these are all neutral, right? Because they have the same number of protons in the nucleus to electrons in the orbit. Once we start taking off those electrons off of atoms or giving electrons to atoms, that's when we're going to start to get these ions because they have a different number of protons to electrons. And so we're going to get some charge creation here. Okay, so that's what an ion is. We're going to fill out the table below, and then we'll draw out, or we'll just show you the ionic bond between NaCl. And then the reason that these are not going to be the best to build molecules and cells because they are able to be dissolved in water. So we're going to look at that quite a bit in the next chapter. What happens is when we fill and we create these bonds here, like for example NaCl, they're charged. And so water is also going to be a polar molecule. We'll talk about why that is. And water is polar, so it's able to interact with charged molecules to separate them. And so we, for example, when we're building molecules in our cells, we want to build molecules that are covalently bonded and not necessarily ionic bonds, because ionic bonds are like salt, they're able to dissolve in water, and we don't want to dissolve our molecules. So when we start getting into chapters like 5 and 6, and we're looking at actual molecules that are being built in our cells, we're going to see that most of these molecules are going to be built from very strong covalent bonds as opposed to ionic, because we don't want to be able to easily dissolve them. All right, so a cation, we said, is a positively charged ion. An example of that would be like Na plus 1. And then anion is negatively charged. An example of that would be the Cl minus 1. Okay, cool. So let's take a look at how this works. So we got this guy here. So do an example. So if we were in class, I would have you guys stop and draw this out. So I think it's definitely a good time if you want to pause this lecture and then go ahead and try to draw that out. And then once you're done drawing out the NaCl example, you can take a look here. And so this is how NaCl works. And so this is the generation of ions, and this also forms an ionic bond. So I went over this with you guys a minute ago, but just to take a look again, remember when we're mixing the element or the atom Na and the atom Cl. So Na is not electronegative at all because it only has, first of all, it's over here on the periodic table. Remember we said that electronegativity increases up here. So Na is 11. Na's atomic number is 11. We look at that, it means it has 2 in the first shell, 8 in the second shell, which equals 10, and then 1 more in the outer shell. So it's 11. So it's not electronegative at all, right? Because it only has 1 in its valence. So it's like, I don't care, get rid of that electron, give it away, because there's no way that it's going to be able to get 7 more. So it's like if I give this away, I expose my lower shell, which has 8, so it's happy and complete. Okay, so sodium is not electronegative. Then let's take a look at chlorine. So chlorine is over here, super electronegative, because it's in column 7, which means it has 7 in its valence shell. We also know that because the atomic number is 17. So if we look here, it has 2 in the first shell, 8 in the second shell, which is equal to 10, right? 2 plus 8 is 10, and then 7 in its valence, right? For a total of 17. So it's super electronegative, one, because it has so much electronegative charge, electronegatives, right? And it also only needs 1 more electron to be happy. So that's why it's super aggressive. So what goes on here is chlorine steals that electron from sodium, it's happy, and it becomes Cl minus 1. Cl minus 1 now because it has 1 extra electron than it normally had. So it's more negatively charged. This is an anion. And remember I said an anion is a negatively charged ion. Sodium becomes plus 1, right? Because it's more positively charged because it lost an electron. Okay, so this forms a cation. So now the association or the attraction of a cation, a positively charged ion, and an anion, a negatively charged ion, comes together to form an ionic bond. Okay, so that's how that all works. So now, like for example, if we look at this, and I'm going to actually come back here. So let's take a look at this here. So what about if we did? Let me do this. We'll try this. Okay, so Na, sodium. We've got sodium's atomic number is 11, and its atomic mass is 23. Okay, so how many protons are in sodium? I'm trying to do these proteins equal. Okay, so how many protons are in sodium? If its atomic number is 11, it has 11 protons equal 11, electrons equal 11, and then neutrons equal 12, right? Because its atomic mass is 23. So we see that? Okay, so protons are 11, electrons are 11, and neutrons are 11 because 11 plus 12, because 11 plus 12 is 23. Okay, so that's our number. Now what about if we're looking at Na plus 1? What happens here? Because now this formed we formed ion. So our protons are going to be the same. Protons equal 11. Electrons now equal 10. And our neutrons are the same, equal 12. And if we went ahead and we looked at this, or actually, I mean, I can draw this out, but you know that these drawings with this little tool are never very easy. But if we have this, we had, and I'll draw it out, or I'll just show you on this one. So here, originally we said that our neutrons and, our protons and electrons of sodium are 11. So if we look here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's 11 electrons. But now it gave it away, gave that 1 electron away. So now in Na plus 1, it only has 10 electrons. So this is the key here when we're looking at our electron number. Okay, and so that's why it is now plus 1, because it is more positively charged proton compared to the electron negative. So it's plus 1 because it's more positively charged. Chlorine, if we look at that one, chlorine had how many in its valence shell? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So it had 17 up here. So 17, and then now it gains 1 more electron. So now it's going to have 1 extra one, right? So that's where we're getting those numbers from. So a good application type question here will be calcium has an atomic number of 20, an atomic mass of 40. How many electrons are found in a Ca plus 2 ion? So normally we said that calcium has an atomic number of 20, which means it has 20 electrons. And now if it becomes more positively charged by 2, how many electrons is it going to have? 18. Okay, so make sure that you're understanding that and you're not drawing. I've seen several times students will put 22, but that's not correct because remember we're becoming more negatively charged. So negatively charged, or in this one, you're becoming more positively charged, sorry, because you're losing those 2 electrons. So now you're going to become 18 as opposed to 20. Okay. If it said 22, then that meant that you became more negatively charged. Okay, all right, so we're almost done with this chapter. A couple other topics to talk about. So now that we know all about ionic bonds, now we're going to look at a covalent bond. We already said that what is a molecule? A molecule is basically when just 2 atoms come together in association to form a molecule, and that is for purposes of filling those valence shells. So a molecule is when we just have 2 or more atoms in association, and a compound is when you have different atoms in association. So for example, we looked at, H2 gas or O2 gas. Those would be molecules, but things like the sodium chloride or water, H2O, those are also molecules because you have atoms in association, but now they're considered a compound because you have 2 or more different atoms. Okay, so that's the difference between a molecule and a compound. So a molecule is like, we'll say 2 plus atoms in association, and then for example H2, and then a compound is 2 plus different atoms. For example, H2O, or NaCl. Okay. All right, and then looking at our different types of bonds. So I already showed you guys the ionic bonds, right? And so how we form molecules, you can either form molecules or the atoms can come together to either form an ionic bond or a covalent bond. So we saw the ionic bond already, and we've also kind of saw the covalent bond. So ionic bond is when you have the opposite charges attract, and a covalent bond is where they share a pair of electrons. So we already saw this, which would be the example of the ionic bond, right, because of their different electronegativity values. And then I also drew out this one with, or didn't I do this one? Hydrogen bonds, the H2. I did that somewhere. The H2 gas, I don't know where that one went. I think that was maybe on the follow along guide, but remember that was an example of the covalent bond, the H2, when I draw out the hydrogen and the hydrogen. Okay, so that's the difference between an ionic and a covalent bond. Okay, so now let's take a look at how we would specifically see the covalent bonds. All right, so that's ionic and covalent bonding. Okay, and we already looked through all this one. And we said, for example, these are really strong bonds, but they're not going to be the best and ideally suited for bonds or molecules in human or in cells because they can be easily dissolved in water. And we're going to look at that property of water in the next chapter of why water is polar and why water is able to easily dissolve molecules. Okay, this question here addressed, which of the following elements or atoms on the periodic table would most likely form an ionic bond. And these ones, again, we've already stressed this a couple times before, that the atoms are going to have to be much differing in electronegativity values. So for example, here, sodium chloride or lithium and fluoride, because those are going to be much different electronegativity values. So they're going to have different interactions with the atoms that they come upon. All right, so then looking at a covalent bonds. Covalent bonds, we said, are when atoms share a pair of valence electrons. Okay, here's my H2, the one that I was trying to find that I drew out. This is 2 hydrogen atoms that have come together in a covalent bond, so they're equally sharing this. And covalent bonds can be between more than 1 pair of electrons. So you can have single covalent bonds, double covalent bonds, and even triple covalent bonds. And these are going to be much more stable, and the bonds that you will see come together to form the bonds in living cells because they're super strong and they're not able to be easily dissolved in water. And we are mostly all water, so this is a really important concept. So let's take a look at some double and triple bonds. So here we've got a single covalent bond because they're sharing 1 pair of electrons. Because remember, hydrogen's atomic number is 1, right? Which means that it has one proton and one electron. So this is one hydrogen and this is one hydrogen. Hydrogen just needs one more. So if you bring together two hydrogens, they each donate one of those electrons and they just share the pair. So they're super happy, right? Because they only have that first shell, which only needs one orbital and only needs two electrons. So this is an example of a single covalent bond, okay? Now let's look at double covalent bonds and a triple covalent bond. So if we were in class, I would have had you guys draw out O2 gas and N2, so oxygen gas and nitrogen gas. Oxygen gas produces a double covalent bond, and nitrogen gas produces a triple covalent bond. So if you want to take a second to pause this and try to do O2 and N2, you can, or if you just want to take a look here, I've got the single bond O2, or a single bond, sorry, H2, which we just looked at, they're sharing one pair, and then oxygen gas, they're sharing two pairs of electrons, because if we remember, oxygen's atomic number is 8, which means that it has 2 in the first shell and 6 in its valence shell. Because 2 in the first shell, 6 in its valence, 1, 2, 3, 4, 5, 6, which means it's deficient in 2 electrons. So these can come together in this formation and share 2 pairs of electrons. But now everyone is happy because what happens is it goes like this. We've got this guy sharing those, and this guy like that. So you see, this is how they share. 1, 2, 3, 4, 5, 6, 7, 8. Happy. 1, 2, 3, 4, 5, 6, 7, 8. This one's happy. So everybody's happy in a double covalent bond. Okay, and then nitrogen, I guess I thought I had nitrogen in here. Nitrogen is a triple covalent bond. So let's see if I can easily draw this one out. 1, 2. So each of these are little bonds. 1, 2. Okay, so when you look at this would be 1, and they're sharing now 3 pairs as opposed to 2 pairs. And so we think 1, 2, 3, 4, 5, 6, 7, 8, nitrogen's happy. 1, 2, 3, 4, 5, 6, 7, 8, this nitrogen's happy. So this is N2 gas. So this is a single covalent bond, double covalent bond, triple covalent bond. Okay, cool. All right, so then on the periodic table, I have these. Oh, I didn't have it drawn out there. All right, so the type of bond that is created, this is a covalent. So hopefully at this point now you're easily seeing the difference between the sharing that goes on in something like this, right? They're sharing these as opposed to the bond that happened in a covalent or an ionic bond when there's like loss of an electron or gain of an electron and those ions are formed. Okay, so again, this is like really basic chem. Hopefully it's all a review at this point. Chapter 2 is usually a review for most people. So covalent. Number of bonds created here would be 1. This would be 2 bonds, and this would be 3 bonds. And then number of electrons shared. So remember, between each bond, you share 2 electrons. So here they're sharing 2, here they're sharing 4, and here they're sharing 6. Okay, because look, here they're sharing 2 electrons, 1 bond. 4 electrons, 2 bonds. 6 electrons, 3 bonds. Okay, so hopefully you saw that. All right, so then what is the difference between a polar and a non-polar covalent bonds? This is just showing you some more types of covalent bonds. Skip this one. I'm going to skip a couple of these to come back to this one. Okay, so then now what is the difference between non-polar and polar covalent bonds? So this is going to take us into the next chapter, which is pretty much going to be the whole premise of chapter 3 and even chapter 4 of what is polar covalent bonding and water. So the degree of sharing can be different in a covalent bond. So sometimes the electrons are completely equally shared. So what you saw here in these examples, this is completely equal sharing, right, between the two atoms. This is a polar covalent bond, equal sharing. Non-polar covalent bond, equal sharing. Now, a polar covalent bond is when the electrons are not equally shared between the two atoms that are involved. And this has to do with if one of the atoms is slightly more electronegative than the other atom. So in this case, we have oxygen and oxygen. So the electronegativity is the same, right? They're the same atom. Hydrogen, electronegativity is the same, equal sharing, non-polar covalent sharing. Nitrogen 2 gas, also equal sharing, the same atom. Now, what about if we start talking about a molecule like water, H2O? Well, if we look at this, back onto our electronegativity values, oxygen is an electronegativity of 3.44 and hydrogen is 2.20. So in that case, when oxygen and hydrogen come together, it does form a covalent bond because it's in this range, if you remember back on the chart that you did, but it becomes something called a polar covalent bond because oxygen is more electronegative than hydrogen. So even though it's sharing the electrons with hydrogen, it kind of wants to steal them. So the electrons start to hover closer to the oxygen molecule or oxygen atom as opposed to the hydrogen. And so it becomes something called a polar covalent bond, which does not produce the total charges that you see in ionic bond, but it produces a partial charge, which is why we end up getting something called polar covalent. And polar, if you think about like the poles of the planet, or poles of the battery, they're charged. So we end up getting like a partial charge on a water molecule, which is why water is able to dissolve things, right? Because water is partially charged, okay? So I'm not gonna get too much into that now because that is gonna be the whole topic of the next chapter, but I just wanted to introduce it now. What is the difference between non-polar and polar covalent, right? Because it kind of follows up with the covalent bond types. Okay, so then looking at what is the difference between non-polar and polar covalent bonds. So nonpolar is equal sharing of electrons between the atoms involved. And a polar covalent bond, so and an example of this one, example would be O2, N2, H2, all those that we looked at. And then a polar covalent bond is unequal sharing of electrons between the atoms involved in the molecule. And an example here would be water. That's going to be like our most used example here in this class, water. Okay, cool. All right, so then one other thing are actually redox reactions. I'll mention to you what I have here is a redox reaction is another type of reaction. So I just threw that in here because it's chemistry. We're going to talk about this a lot more in later chapters, so I don't want to get into this too much right now, but a redox reaction are going to be the basis of our energy harvesting reactions, and redox reactions are reactions that relocate electrons between atoms. So you can think about them kind of like the ionic bonds because they are, they're going to be similar to that, where electrons are completely stolen from certain atoms and then donated to other atoms. So we're going to see this quite a bit. So just for right now, just kind of remember that redox reactions are going to be the basis of our energy yielding reactions, and they are reactions that relocate electrons between atoms. And they've got two different considerations here. So atoms that gain electrons are called reduced atoms, and atoms that lose electrons become oxidized. Okay, so oxidation is the loss of an electron, and reduction is the gain of an electron. So I'll just jot that in here. What are redox reactions? Redox reactions are reactions that involve movement of electrons between atoms, and loss of an electron equals, all right, this is called oxidation, and gain of an electron is called reduction. Okay. And then I'm going to skip these things for right now. We'll talk a little bit more about this in the next 2 chapters about like a molecule shape and how it interacts. So it's kind of getting ahead of ourselves. So we'll talk about that in the next chapter. And then the other thing here is just the chemical reactions. Chemical reactions are making and breaking of chemical bonds. So this we've kind of already seen, before, where we have our reactants, and then bonds will be formed to produce products. So for example, like how do you form H2O molecules, right? You bring together hydrogen and you bring together oxygen, which are our reactants. And then you end up having some kind of a reaction, and then they will form a product, right? And you get your H2O molecules. And that's when we're forming bonds. And then we can break bonds by taking a product and breaking the bonds, right, to get back your reactants. Okay. All right, so let's take a review here. So let's review. We've had you guys do this as a group in the class, but let's do it right now. So looking at the periodic table, find the element with the atomic number 11. So let's go ahead and do that. So our atomic number 11, where'd that be? And they go in order. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we see here sodium. Okay, so our atomic number element with 11 would be name, sodium, and symbol is Na. Okay, number of protons, neutrons, and electrons. So if its atomic number is 11, remember that tells us our number of protons, so that's going to be 11. And then that also tells us our number of electrons if it's neutral, because Na is neutral, there's no positive or negative, so that's 11. And then the number of neutrons is going to be 12, because our atomic mass is 23. So it says 22.9, but remember we want to round that up to 23. So 23 minus 11 is going to be 12. So neutrons equals 12. Atomic mass, mass number, we said equal 23. We already said that. How are the electrons arranged in energy shells? That is like this. I'm not even going to try to draw this out again on that page. Sodium, remember we have 2 in the first shell because we've got 1 orbital. And then there's 4 orbitals in the next shell. Each can hold 2. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1 extra one for the 11 in the third shell. So that's how they would be arranged in the energy shells. So it would be like this. It's going to be 2, 8, and 1 for a total of 11. Then the number of valence electrons is going to equal 1, because remember valence are the electrons in our outer shell. The type of bond it's most likely to form, remember, ionic, because it's not electronegative. Right? Because there's no way that it's going to be able to fill up that valence shell, right? If it has only 1 in its valence, there's no way it's going to get 7 more. And it's not going to be able to like share. It can't form a covalent bond because that has to be an equal sharing. It's not going to share 7 electrons. So it's going to form mostly an ionic bond, so it can just give away that electron. Okay, an isotope would be possibly Na if we're 23. Remember that isotopes are atoms that have a different number of neutrons. So if normally it would be 23, what about like Na24, Na25, right? Those would be different types of isotopes because they have different number of neutrons. And the relative electronegativity is very low. And if we go back and find our electronegativity chart, Na is going to be 0.93. So Na, low, and it's 0.93. Okay, cool. All right, guys, so hopefully that was super helpful. Basic review of chemistry. I'm hoping also that that was a good review. I mean, I like to go into this in great detail. I know that there's other instructors that just kind of like skip this chapter or go through it really, really fast because they expect you to already have like a really good base on chemistry. But like I said in the beginning, I think it's really important to have this really strong base. So hopefully that was just a review and that wasn't really challenging. The next chapter we're going to move into here shortly, we're going to go through water chemistry and pH, and then we'll move into the organic chemistry. That maybe is going to be a little bit more challenging. Maybe some of that isn't as much of a review. But again, if this was really challenging of a chapter and this was not a review for you and you have not had chemistry in the past, definitely do not let this slack. Try to get as much help and like grasp on this right now because it's going to really help you throughout the rest of the semester. All right, well, stay tuned for some more chemistry, and I hope you guys will practice all this chem. All right, I will talk to you soon for chapter 3. Bye-bye.